triple integrals using spherical coordinates. Let's review spherical coordinates. The variables are rho, telling the distance to the origin. Theta, copied from cylindrical coordinates, therefore it has bounds between 0 and 2 pi. That is giving an angle with the x positive axis. Phi provides an angle with the z positive axis and has bounds between 0 and pi. You want to recall that x is equal to r cosine theta. Remember that r is equivalent to rho sine phi. Y is the same thing as r sine theta. Z is the same thing as rho cosine phi. Theta is used in both cylindrical and spherical. So if you're translating from spherical into cylindrical, you get to reuse it. On the other hand, to go from rhos and phis and produce a z, you let z equal rho cosine phi. If you want to translate from cylindrical to spherical, you have these identities. It's useful to keep in mind that rho set equal to a constant describes a sphere of radius c centered at the origin. Theta set equal to a constant gives you a half plane. And that phi set equal to a constant will provide you with half of a cone, provided that the c is not pi over 2. Acute angles, you'll get the upper nape, and for obtuse angles, you'll be given a lower nape. All right, so what about integrating? Let's start by looking at a small volume element for a region described using spherical coordinates. We would be measuring changes in rho, changes in phi, changes in theta, but we pick up a multiplicative factor, rho squared sine phi. Then in the limit, that translates into a volume differential where you have d rho, d phi, and d theta, and then this Jacobian of rho squared sine phi. The default order is to first integrate with respect to rho, followed by phi, and then typically regions are easily understood to have hard bounds on the theta. So let's do an example of setting up a triple where the region is described in spherical coordinates. Let's take two surfaces, one a cone and the other a hemisphere. The cone is pictured here in red and the hemisphere in blue. Those two will capture a solid, let's call it E, that is like an ice cream cone. If we were to, so that ice cream cone will make a full circle. If we pick a point and walk around, we'll get a full circle, so 0 to 2 pi on theta. Now, if we set theta to some value, for example, if we chose pi over 2 for theta, that would describe the xy half plane, which I've drawn over here, the upper half plane. And then it will intersect with the sphere in this line here, rho equal 2. That half plane will intersect with the cone in this line here. And then I've shaded in blue the cross section of the solid E we're trying to describe. So since this is representing z positive, phi would form an angle of 0 if we want to point in the direction of z positive. So that's going to be a lower bound on phi, since that corresponds with the blue shaded region. And then we want to look at opening up an angle phi as we move away. And we'd want to move away until we get to the cone. So that value of phi needs to be determined. Since phis are going to open up until we get to that red cone, let's take the equation for that red cone and change it from rectangular coordinates into spherical coordinates. So here's the equation of the surface, which is the cone. Change out z, change out x squared, y squared, which is r squared. Do a little bit of algebra, apply the radical. And then sine phi over cosine phi is tan phi. The rows cancel out. We want to bring the rad 3 to the other side. So we got 1 over rad 3 as tan phi. In other words, phi can be as large as pi over 6. So that's providing us with our upper bound on phi. Lower bound 0, upper bound pi over 6. To correspond with this cross region, cross section. Now pick an arbitrary value phi between the small value and big value. Let's call that phi sub 1. Find all points on that ray that correspond with the shaded blue region. We then have a small value for rho of 0. And then the furthest distance that we can move away would be out to the sphere of radius 2. Hey, look at that. We have inequalities for all 3 spherical coordinates and thus have described our solid E. We read from the bottom to the top in coming up with our volume differential. And we recall that we need to tack on this Jacobian of rho squared sine phi to the product of d rho, d phi, d theta. Using our inequalities and this volume differential in spherical coordinates, we can easily set up our triple that's going to provide the volume of our solid E. Beautiful.